In this video, I want to review a little bit about experiment design, and with a question from 2003, and then I want to do some more probability, which is going to lead us into kind of the first 5 rules of probability, which you'll see in the next video. Because of concerns about employee stress, a large company is conducting a study to compare 2 programs, Tai Chi or yoga, that may help employees reduce their stress levels. Tai Chi is a 1,200-year-old practice originating in China that consists of slow, fluid movements. Yoga is a practice originating in India that consists of breathing exercises and movements designed to stretch and relax muscles. The company has assembled a group of volunteer employees to participate in the study during the first half of their lunch hour each day for a 10-week period. Each volunteer will be assigned at random to one of the 2 groups. Volunteers will have their stress levels measured just before beginning the program and 10 weeks later at the completion of it. A group of volunteers who work together asked to be assigned to the same program so that they can participate in that program together. Give an example of a program or a problem that might arise if this is permitted. Explain to the volunteer group why random assignment will address the problem. Well, I think the biggest thing here, if maybe we can just kind of draw a line down, the biggest problem is you would assume that these people are asking to be assigned together, that they're friends, and they may have similar stress levels and similar jobs, and may work in the same part of the company. They may have the same exercise lunch because they're friends. So you wouldn't be necessarily getting a good cross-section in a group. So that's probably how you'd explain it to them. And remember, random assignment, the reason we use it is for generalizing. So the minute we don't use that, we lose the ability to generalize at all. Okay? Someone proposes that a control group be included in the design as well. The stress level would be measured for each volunteer assigned to the control group at the start of the study and again 10 weeks later. What additional information, if any, would it provide? Well, obviously with a control group, it's always nice to have just baseline comparison data. And the reason it might be important here is, like, imagine this company, we don't know what they do. Imagine they're a tax company, and we start our study in March and end it 10 weeks later. Well, if it's all through tax season, I bet everyone's stress level goes down after April 15th. So the reason we always want to have a control group is it's always nice to have baseline data for comparison. Okay? And I'd probably say more about that, why. In general, stress might decrease for everyone in the company, right? It might not be the program. Okay? Is it reasonable to generalize the findings to all employees of this company? Well, the real problem here, we can talk about random assignment. We can talk about the fact that is good. It does help generalize. But the problem is that these are volunteers. Okay? So the answer here is no, and the explanation really is, once you've used volunteers, you're not doing any kind of random sampling. So these people might be really interested in learning how to do yoga or Tai Chi. This is something they want to do during their lunch hour. So you can't generalize to all employees with this sample. Okay, let's move on. So I just want to start making the link here between probability and statistics, because there is an important link. And what probability does for us is really 2 things. It lets us know if our sample or our results that we're looking at were probable or improbable. And that gives us 2 things to think about. Was our sample biased? If it shouldn't have happened, if according to probability our sample shouldn't have happened, is there something wrong with our sample? Have we picked a biased group? On the other hand, maybe our original baseline data that we're comparing to is no longer valid. For example, the Joe Mauer example we did a few days ago with the .308 batting average. that's from a long career. Okay, so if all of a sudden we start taking a sample of his batting average and we look at, a couple of months and he's batting 250, we can either say this is just a bad 2 months, it's a bad sample. Or we say maybe that 308 is not the level that he's playing at anymore. So probability gives us a gauge of how likely events are compared to old data. I want to do a little work here with just looking at simple probabilities. And as I said, this is going to lead us to some kind of rules about probability that we're going to look at in the next video. So we talked a little bit in a previous video about sample spaces. Sample spaces are simply a list of all the possible outcomes. And you can see I've picked two pretty simple and common probability examples here: flipping 2 coins, rolling 2 die. And I've found pictures that represent the sample space. So of course these are the outcomes. Either both coins are heads, first is heads, second tails. I guess the first is tails, second is heads, or they're both tails. So when you flip 2 coins, I want you to think about, the probability of an event is really how many times do we have success, or what we're looking for, out of the sample space. So the probability of getting 2 heads is 1 out of the 4 possible outcomes. Okay, so I'm going to write 1/4. The probability of 2 tails, once again, we have 1 outcome out of the 4 in the sample space. Only 1 deals with 2 tails, so 1/4. And then finally 1 tail and 1 head, and notice I didn't say in order. Okay, so it could be the first one's a tail, the second one's a tail, or either one. This is the other 1/2. These 2 outcomes that have a mix. So when you flip 2 coins, it's more likely that they're different than that they're both heads. Okay? Now, rolling 2 die. You see I found a picture that has a red and a green, so you can see there is a designation here between 1-2 and 2-1. Okay, much like up here, there's a designation with these coins. So the probability of rolling doubles. Well, you'll notice there are 36 possible outcomes. Of course, this diagonal represents doubles. So that is 6 out of the 36. And I'm going to write 6 out of 36. Well, I'm going to try. 6 out of the 36. And then I will reduce that to 1/6. Okay? Rolling a sum of 5. Okay? So let's just look for ones that would add up to 5. Of course, we've got 1 and 4, 2 and 3, 3 and 2, and 1 and 4. So this diagonal adds up to 5. So 4 out of the 36 outcomes, or 1/9. Okay. Rolling a sum of 7. Okay, so now we look for this: 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. So this diagonal right here, these 6 possible outcomes. So once again, we have 6 out of 36, or 1/6. And finally, rolling a sum of 1. Well, there is no way to do that, right? If you roll 2 dice, the least amount you could possibly get is 2. So this one will be 0. All right, and the last piece of probability, kind of introduction stuff before the rules I want to talk about, really deals with multiplication principle. I always call these problems slot problems because I think about how many things would fill the slot I'm looking for, and I'll explain that in a minute. A password is to consist of 2 numbers and 1 letter. Okay, so again, let me explain what I mean. Your password has 3 slots. And assuming it's just a number, like a 10 digit, 0 to 9 number, there are 10 possibilities in that first slot. And in the second slot, again, assuming you can repeat because you picked 1, you can pick 1 again. Once again, we have 10. And then a letter. So there are 26 possible letters. So if you multiply this, 10 times 10 times 26, that is 2,600 possible numbers. So if you have a password that consists of this, and I didn't say, but 2 numbers, please. What I meant was a number that's between 0 and 9. Of course, obviously, if it was any number, we have an infinite number of choices. I have 2,600 outcomes in my sample space. So if someone walked up and guessed my password, I would think that they, have a 1 in 2,600 chance, or probability of 1 over 2,600 probability of getting that password right on the very first try. So multiplication principle is the idea that we can use multiplication to count the number of outcomes in the sample space, so we don't necessarily have to list a whole space out. The previous examples with the coins. Think of 2 coins as, 2 slots. Each one heads, tails, so it's 2 times 2. It's 4. You've got 2 dice. You're rolling 2 dice. Each dice represents 6 things that go on the slot. 6 times 6 is 36 possible outcomes. And this, I think, leads to just kind of a fun look at how many Social Security numbers are possible. Now, if you know how Social Securities work, they actually don't allow you to have 0 in every spot. There are some rules that gauge. In fact, the lowest first 3 is 0, 0, 1. But I said how many are possible, meaning if they're running out of numbers and say, we need to open up 0 through 9 in every slot on the Social Security number, how many were possible? So let me just give you an idea here. 10 times 10 is 100, 1,000, 10,000, 100,000, 1 million, 10 million, 100 million, 1 billion Social Security numbers. And if that doesn't seem like a lot to you, the Social Security system has not been around that long. That is an awful lot of Social Security numbers. We are in the United States nowhere near reaching that 1 billion mark.